Okay, now we are going to look at this example here, problem from all the exams. It says 2-point charges, they lie along the x-axis. So the first thing you have to do, my son, is draw your x-axis here. And you need two charges. One of them is Q1, is located at the origin. If this is my y-axis, that's the origin here. So I have a charge here, Q1. I'm going to write here Q1 here, put it here. So Q1 is equal to 2 plus 2Q. Okay, all right, that's Q1. And the other is located at x equal 5 centimeters. So if this is 1, 2, 3, 4, 5. So my charge Q2 is here, okay, at 5 centimeters, Q2, okay? And I don't know what is its value here, huh? Q2. Now, if the electric potential due to the two charges at x equal 4 centimeters, it means here, at this point P, is equal to 0. The potential there, so it says that the potential at point P is equal to 0. What is the magnitude of the sign and sign of Q2? So they want what is Q2, the magnitude and sign of Q2. That's the question, okay? So he gave you the potential at point P due to the two charges, and he asked the value of Q2, which is going to make the potential here equal to 0, okay? If you change the value of Q2, the potential will be different. There's only one specific value of charge Q2, which is going to make the potential at point P to be 0. Now remember, my son, that the potential is a scalar, and this makes life easy for you because it's easier to deal with scalars than to deal with vectors. Vectors, they need, especially when it's not a one-dimensional like here, it's one-dimensional problem. But vector is very difficult to deal with vectors because you have to look at the components and so on. Here, there are no components. I remind you, the potential due to a point charge is K Q over R. This is the potential due to a point charge, okay? Potential due to a point charge, Q, okay? Q. And this is the potential at distance R from the point charge, okay? Now, let's apply this here. We have a system of particles. We have two particles at this point. So let's apply that, okay? Now, the potential at point P, due to the two charges, will be the potential of this charge here and the potential of this charge here. What is the potential of the charge Q1? It's K Q1 over the distance. Let's call this one x1, okay? x1, we know the value of x1, it will be 4, all right? It will be 4 centimeters. Okay, 4 centimeters, okay? And plus k q2 over x2. And the distance x2 will be what? According to the figure here, it's 1 centimeter, okay? So we know the value of x1 plus, and this is equal to 0. This has to be equal to 0, okay? So if this is equal to 0, it means that k q1 over x1 plus q2 over x2 has to be equal to 0. Since k is not 0, we know the value of k. It means this is equal to 0, okay? So from there we get q2. We are looking for the charge q2. Q2 will be what? Minus q1 over x1 times x2, okay? Let's put the numbers there. Minus q1. Q1 is what? Is 2q, okay? 2q. x2 is what? Is 1 over 1 centimeter, of course, over x1, which is 4 centimeters, okay? 4 centimeters. Of course, centimeter will cancel, and you get minus what? Minus 2q. And this is the final answer for this example here. The final answer, okay, for this example. Now, remember that you notice that the charge Q2 is going to be negative, okay? Okay? Otherwise, you cannot have the potential equal to 0. If this charge was positive and this is positive, it will never make the potential here equal to 0 because you see here, if both charges are positive, this can never be equal to 0. See, if this is positive, this has to be negative, okay? That's very important to look at. So the charge Q2 has to be negative to make the potential between them at this point here equal to 0. It has to be minus 2q, okay? So if this is plus 2q, minus q over 2, it's minus q because 2 over 4 will give you q over 2, okay? Be careful, minus q over 2, this is the correct answer, okay? It's not minus 2q, it's minus q over 2. Thank you. Okay, let's look at this example related to a potential, electric potential due to a system of charged particle. Okay, it says a square. Okay, so you have to have a square here. So we make a square here. That's my square. Okay, it has equal sides of length 1.3 meter on each side. That's a square, 1.3 meters. Okay, and this square has 4 particles fixed at its corners. Remember, they are fixed. Okay, so I'm going to fix them. Don't worry about the way to fix them, why they are fixed, and so on. Just try to solve the problem for the time being. And I have a charge Q1. Q1 here is equal to 12 nanocoulomb. Remember that nanocoulomb means 10 to the power minus 9 coulomb. This is very important. Microcoulomb, it means 10 to the power minus 6 coulomb. And picocoulomb, it means 10 to the power minus 12 coulomb. Okay, so remember these things. Okay, all right. So nanocoulomb, that's the charge Q1 there. Charge Q2 here is equal to minus 24 nanocoulomb. This is positive charge and negative charge. And Q3 here, Q3 is plus 31 nanocoulomb. And Q4 is plus 17 nanocoulomb. So he gave you the charges in the corners of this square. Okay, he gave you the different charges. They are not equal charges, but it doesn't matter. Q1, Q2, Q3, and Q4. Okay, and he wants what does he want here? Calculate the electric potential at the center of the square due to the 4-point charges. So he wants the electric potential at the center of the square. To find the center, you draw the 2 diagonals, and where they cut the diagonal cross, that's the center here, point P. Okay, I'm going to call it point P. Okay. Now, so you remember that the potential V is equal K Q over R for any point charge. R is a distance from the charge to the point where you want to calculate the potential, electric potential. I want the potential at this point, so this is my R. So this is my R here. And R is the same for all charges. You agree? That's the half of the diagonal here. Okay? So how many potentials I have to write here at point P? I have to write 4 potentials. So V at point P will be K Q1 over R, this distance, plus K Q2 over R, plus K Q3 over R, plus K Q4 over R. And R is the same for all of them. It is half the diagonal. Okay? And he gave you the side, so you can find easily this half diagonal. Okay? Now, when you put the charges, you have to put them with the signs, because this potential is a scalar, so you have to put the charges with their sign. If the charge is positive, then you put it positive. If the charge is negative, you put it negative. Not like the electric field. The electric field, you put the direction vector and you put the charge in magnitude in the equation. So here you have to put the sign because we are dealing with the scalars. Okay, this is algebraic sum here. Be careful. Okay, let's calculate this R here, which is this distance here, half the diagonal. As you know, we are going to use Pythagoras. This is 1.3 meters, 1.3 meters. So the whole diagonal here is square root of this. You square this, and take the square root, so you get this here, 1.3 square root of 2 meters. And I want actually half of it. I want this distance here. Okay, so that distance there is 1.3 square root of 2 over 2, which is 1.3 over square root of 2 meters. That's the distance R. So R in this problem is 1.3 over square root of 2 meters. You have to know how to do this, my son. This is very important. Okay. So I know R, I know Q, and I know K, so I can find now the potential at point P is 9 10 to the power 9. I put it common factor over R common factor 1.3 and take the square root of 2 there, because it is down here, so it becomes square root of 2. And then I open the bracket here to put the charges. Q1 is 12 nanocoulomb. Okay. Now Q2 is negative, minus 24 to the power minus 9 nanocoulomb. And then Q3 is positive, plus 31 to the power minus 9. Don't forget this minus 9. Plus 17 to the power minus 9. So this minus 9 cancel with this 9 here, okay? And you end up, if you do the correction, the calculation correctly, you end up with the potential equal to 342 volts. That's the potential at point P, and it is positive potential, okay? At point P, okay? At this point, the potential is 342 volts. That's how you calculate the potential for a system of particles. Here we have 4 particles sitting in the corner of a square, and the potential at that point in the center of the square is given by this value here. Thank you.